not to forget. Yeah, so yeah, before we start, I just want to briefly recall that last time we were working on generating functions, both the usual ones and the exponential ones, and they will reappear in our lecture course quite soon, because in particular recurrence relations also provide a way to get a generating function for the sequence of numbers which recurrence relation generate. So we were discussing the summation operator, which is a way to get from the usual recurrence, from the usual generating function, the generating function for consecutive sums of numbers in our sequence. And then we're discussing exponential generating functions, which are usually more useful and applied when we're counting objects where the order in which they appear is essential. Okay, so let me share my screen and we'll start discussing recurrence relations. Please check your network connection. Yeah, now, okay, good. Yeah, so I'll start with certain general definitions of recurrences, and then we'll concentrate today on the simplest case, linear recurrences of order 1 and 2. And for order 2, we'll be mainly working with linear homogeneous recurrences with constant coefficients, which is really a very simple situation. And they are quite similar in many ways to things which you might know from your calculus class, which is linear differential operators with constant coefficients, homogeneous linear differential operators with constant coefficients. Okay, so what is a general recurrence relation? So a general recurrence relation is, so we have a sequence, so a sequence of numbers, say A1, A2, A3, and so on, such that there is some procedure which enables us to restore the next number such that there exists a procedure allowing to get an using all the previous ones, all the previous numbers. So A1 through n minus 1. If we in fact need just a fixed number of previous numbers, so if this procedure requires k previous numbers, then we say that we have a recurrence of order k plus 1. In other words, so we have some recipe allowing us to express the next term an using some function of a minus 1, a n minus 2, and so on, a n minus k. So where there is a dependence, in other words, between k+1 consecutive entries in our sequence. That's why we are talking about recurrences of order k+1. There is a relation between k+1 consecutive numbers in our sequence, and we can, for each position, so to say, for each n, we can express a n using k previous guys.
What's the order if we use all the previous numbers, as you said first?
Yeah, well, there is infinity in principle. And recurrences which require usage of all the previous numbers are rather clumsy. They sometimes appear, but that's, yeah, I also in particular had such situation in my own research. But this is usually not what we want. So at least I don't know if there is a general theory of such recurrences, but usually they are not very useful. So a useful situation is that it appears if only a fixed number of previous entries are required to restore the next one. Okay. Okay, so again, this is a fairly general situation. It's some kind of dependence, and this is still quite difficult to study in general. What is good? What is a good object of study is linear recurrences. Linear recurrences. So linear recurrences of order k+1. These are, in other words, things like C0, a n plus k, okay, n plus k+1. I'll be shifting my indices a little bit, plus C1, a n plus k plus C2, a n plus k minus 1, plus ck a n, I guess, equals some number bn. So these, in principle, these can be, again, so these guys can also depend on n. So these, I'll put the indices here. So we have a linear non-homogeneous, in general, non-homogeneous equation satisfied by k+1 consecutive entries. The coefficient of such a recurrence can in principle depend on n also. So, but the situation is much better if at least coefficient c are independent. So, so we say that a linear recurrence has constant coefficients if ci's and b are independent of k, or independent of n, I'm sorry. And this is the best situation. This case is really completely studied, and that's what we'll be going to do. Because in situation of linear recurrences relations with constant coefficients, everything can be worked out completely, all formulas, and we can get nice analytic expressions for linear recurrences. One more observation I want to make remark. Solution of a recurrence of order k plus 1 depends in an essential way, depends essentially on the choice of the initial conditions, of the starting values or initial conditions, which are, say, A1, A2, A3. We have to prescribe k first guys. And then using our recurrence, we can start generating ak plus 1, ak plus 2, ak plus 3, and so on and so on. But we need to pick the initial conditions to do our procedure, and we'll have such an interesting example later on in our lecture. We'll see that this dependence is actually quite crucial. Okay, so let me start with a very basic example. It's really quite trivial. So we'll be talking about k equals to 1, which means that the next entry in our sequence is just a certain function of one previous guy, just one. Okay, so we'll think about geometric progressions here. What is a geometric progression? A geometric progression is a sequence of numbers of the form, say u times q, u times q squared, u times q cubed, and so on. Well, what do we have? If we denote this guy, maybe, I don't know, A0, A1, A2, A3, and so on, then we have an obvious relation. Simple relation would be that an or an plus 1, the next entry would be just q, a given fixed number, times the previous one. And this works for all n big or equal than 1. So A1 is A0 times Q, A2 is A1 times Q, and so on. So notice that the starting value is important. So in general, we get an equals what? U q power n. And u is essential here. U is kind of the starting value. For different u's, we get in principle different geometrical progressions, although all of them are quite similar. The starting value is still quite important. Let us do one example related to geometrical progressions on one side and to combinatorics on the other side. This would be composition count. So we're discussing this composition count, I think it was a week ago. And I'll recall what a composition is, and we got a very nice simple answer for compositions then. And I now want to rediscover the same result using recurrences. So I recall that a composition of number n is a positive integer, is is a identity, I don't know, identity of the form I1 plus I2 plus da 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 plus IK equals n, where those are positive integers. And the order is important. So, for example, for n equals 3, we have 4 compositions of the number 3. So we get that, yeah, so k here is a variable number. It doesn't have to be the same. So we are looking at all possible ways to represent n as the sum of positive, ordered sum of positive integers. So for n equals 3, we'll get just 3 itself. 3 equals 3. 1 plus 2, 2 plus 1, and finally 1 plus 1 plus 1. We have 4 possibilities, 4 options. And we ended up proving that if an denotes is the number of compositions of n, is the number of compositions of n, then we have the following very simple formula that there are totally 2 power n minus 1 such compositions. So in particular, for n equals 3, we get 4, which I just listed for you above. Okay, let's now try to settle this claim using recurrences. So in order to do this, let's try to understand how we can get compositions of number n plus 1 from those of number n. Okay, proof using recurrence. Okay, to do this, let's look at the situation when we'll be changing n from 3 to 4. So what happens? Now, how to get all compositions of the number 4 from those of number 3? So let me repeat. For number 3, we have 3, 1 plus 2, 2 plus 1, and finally 1 plus 1 plus 1. How would I get those of a number 4? So there are 2 procedures which will allow us to get all compositions of number 4 from those of number 3. One way is increase the last number by 1. And another one, add an additional 1. 1 at the end. At the end. So using these 2 simple operations, we'll be actually creating all possible compositions of number 4. Okay, so if we'll be increasing the last entry by 1, we'll be getting 4 out of 3, 1 plus 3, 2 plus 2, 1 plus 1 plus 2. This is one way. If we'll be adding an additional 1, so we'll be getting 3 plus 1, 1 plus 2 plus 1, 2 plus 1 plus 1, and finally 1 plus 1 plus 1 plus 1. So this will be another 4 tuple. So totally we'll be getting 8. And it's easy to see that this gives us a complete list of possibilities. How? Well, because we can go back. So if we are given a composition of a number 4, so what can we do with that? If the last entry in the composition is at least 2, then we can subtract 1 from it and get a composition of the previous number. And if the last entry in the composition is 1, we can just remove it, this one, just delete it, and get again a composition of the previous number. And if we'll observe, we'll be getting 2 copies of the previous thing. So in this way, we can show that this is actually, these 2 procedures are enough to generate all compositions of the next number. And also it's easy to observe that these 2 operations lead to non-intersecting compositions. Here, with the recipe number 2, we'll be getting all compositions of the next number which end where the last entry is 1. And here, with our first recipe, the last entry will never be 1. It will be strictly bigger than 1. So those things will be disjoint. In any way, from this procedure, it's obvious that we have the following recurrence relation, that an plus 1 is just twice an. So we'll be getting 2 copies of our compositions of the previous number n. And the only thing to do is now to check what would be our starting condition for this recurrence. If we have such a recurrence which works for n bigger than or equal, say, than 2, then its general solution would be a geometric progression with a denominator 2, which means that an equals some number u, which we don't know at the moment, times 2 power n. Now, we have to check what happens to determine u. We need to check, say, a1 or a2, a1 for example. A1, how many ways there are to represent number 1? And number 1, there is just one way to do this. What does it mean? So that a1 equals u times 2. So we'll get u equals to 1/2, or the total answer would be, as was said, an equals 2 power n minus 1. U equals 1/2 leads us to an equals 2 power n minus 1, and that's exactly what we proved earlier, that the number of compositions of a number n is just 2 power n minus 1. This is a different way to do this using recurrences. Okay, yeah. So what would be our next thing to discuss? Another classical example. Before I move further, I want to state another classical example, the Fibonacci numbers. Fibonacci numbers. So they were first introduced by Leonardo de Pisa, which was also called Fibonacci, as early as the 11th century. So he was a very important figure both in mathematics and art and trade and many other things. It's difficult now to estimate his role, at least for non-specialists. But at that point, mathematics in Europe was in extremely poor shape. So in principle, mathematics of Islam countries in Middle East were much more advanced, in particular when it comes to usage of Arabic or Indian system. In Europe, there was still mainly a Roman system was used, which is not a positional system, and it makes it very, very complicated to do simple operations, especially multiplication using Roman numbers is a nightmare. So he was the one who actually wrote the first book explaining how to use Arabic Indian system, decimal system, and so on and so on. In particular, I don't quite remember why he introduced this system, this sequence of numbers, which I'll discuss. His motivation was something about rabbits, how many rabbits you'll get if just one pair of rabbits will start, and then they will be producing one baby or whatever every third month, and so on and so on. So what he started with was, so his sequence was, so the 0th element was 0, the first element was 1, and then after that you have the following recurrence, that the next guy equals the sum of two previous guys. So this works for n big or equal than 2. So if we have these starting values 0 and 1, we can get all the rest of them. So let's do some of the exercises. Let's calculate some of those numbers. So A2 would be, okay, so we'll start with 0 and then 1, and then we'll add up two previous guys. So the next guy would be still 1, of course, then 2, 3, 5, 8. What do we get next? 13, yes, 21, 34, and so on. So this is an extremely important sequence. It shows up in many places in nature. It's closely related to the so-called golden ratio, which is, since the antiques, seems to be the best proportion to be used in architecture, in painting, in sculpturing, and so on and so on. That for some reason this mysterious sequence and related number, golden ratio, appears all over the places. Okay, but I want to point out that, so we have a rather simple recurrence relation, linear homogeneous recurrence relation of order 3, which is of the form an plus 1 minus an minus 1 equals to 0. So this is our basic recurrence relation satisfied by the Fibonacci numbers, and it works for n at least 1. And we have the initial condition a0 equals to 0, a1 equals to 1. These are the initial conditions. So we'll come to this sequence and its modifications a little bit later. So this is a linear recurrence of order 3. So it's 3 consecutive entries which are involved with very simple coefficients. Okay, so now let's discuss a little bit non-homogeneous examples. Non-homogeneous, simple non-homogeneous examples. Non-homogeneous means that it's not that Non-homogeneous examples means that we have of order 2. So in general, it means that we have a n plus 1 equals some constant c, c maybe, a n, and plus some additional number bn. This is not 0 in general, not 0. So if it were 0, then we'll have our geometric regression, if c is a constant, of course. But if we have some additional constant, can be different each time, then we are getting a much more general non-homogeneous recurrence of order 2. Let's consider one nice example, which is kind of motivated by practice. So I'll be talking about the following example: the an plus 1 equals the previous guy an plus n. So bn would be a variable number equal to n. So let's see, let us start with, say, a not a1 maybe equal to 0. So what do we get? And then I'll motivate why this example is interesting. So this is the initial condition. So, and this works for n big or equal than 2. So with this relation and this initial condition, all the sequence of numbers is well defined. So let's do calculate some further guys. Yes, so if a1 is 0, then we have a2 equals a1 plus 2. A1 plus, I'm sorry, 1 plus 1. So which is 1. So yes, n equals 1 here. So look at our recurrence, an plus 1 equals an plus n. Okay, so a3 equals a2 plus 2. So 1 plus 2 is 3. A4 equals a3 plus 3, which is 6. Let's do one more. A5 equals a4 plus 4, which is 10. So we're getting the sequence 0, 1, 3, 6, 10. The next one would be 15. Do you recognize this sequence? So the next one would be 21. Do you have a guess what this should be? And guess is an is actually n choose 2, which is n times n minus 1, 1/2. So let's check that this works. Say a1 vanishes because we have 1 minus 1 here equals to 0. A2 is, if we throw in n equals to 2, we'll get 2 times 1 divided by 2, 1. For 3, we'll get 3 times 2 divided by 2, 3, and so on. So now we can easily prove this by induction. Induction. Say base of induction is a1 equals to 0 both ways. It's easy to check. And then inductive step. So we'll be looking at an plus n, which is by inductive hypothesis n choose 2 plus n. So if we expand n choose 2, would be n times n minus 1/2 plus n. If we write this with a common denominator and factor out n, we get n minus 1 plus 2. Totally we'll get n times n plus 1 divided by 2, which is exactly n plus 1 choose 2. So we're good. Okay, so for example, a sequence of binomial coefficients can be obtained by a linear, non-homogeneous recurrence of order 2. Quite simple. Another situation which might happen is that the constant, say the recurrence is homogeneous, linear homogeneous recurrence of order 2, but the constant we are multiplying by can depend on n. So another case of variable coefficients for order 2 is something like an plus 1 would be equal to some constant alpha, no, say q, which will depend on n, and then times an. So that's a homogeneous case. We don't have an additional constant to add, but this factor is a function of n now. So, for example, if we start with if the initial condition for simplicity is a1 equal to 1, then we get the simple answer an plus 1 would be equal to q1 times q2 times q3 times qn. Yeah, this would be the whole thing. N equals 2, 3, and so on. It would be just the product of those coefficients. So a very basic example is we can get factorials in this way. Say an plus 1 equals n plus 1 times an with a1 equal to 1 will giving us an plus 1 equals n plus 1 factorial. And there are other things like this. So yeah, so there are other examples, not just factorials, there are double factorials as well. There are many coefficients, many sequences can be constructed as a products of a bunch of consecutive numbers. If these numbers are the same, we get the trivial case of a geometric progression, but in general, they don't have to be the same, and we can get some more interesting examples. Okay, let me do a couple of exercises, and then we make a break. Okay, so problems. So exercises. Okay, so I'll be picking number 5 from section 10.1. So it says that the formulation is as follows. Laura invested $100 at 6% interest each quarter. Each quarter means 3 months each. quarter. So the question is, when will her investment double? Investment. So after what number of quarters her initial $100 would be more than $200? Well, I think you have seen such examples already in high school. At least my kids do something like this. So we get a sequence of numbers. So solution. So we start with, say, A0 equal to $100. And then we have the relation. So this is the initial condition. And then after a quarter, after n quarters, okay, so after each consecutive quarter, we get the her previous what she had in the bank multiplied by the interest rate, which is 1.06. Oops, so this should be n plus 1. Okay. So with this recurrence relation, we have the answer, the general answer would be, so we get the geometric progression an equals the initial installment 100 times 1.06 power n, where n is the number of quarters passed since she started that. And so our question is, when is a n big or equal than 200 for the first time? And we can do it using logarithms or just using, I don't know, any basic program. And what I calculated is that n equals 12. So 12 quarters, which means 3 years she has to wait before $100 will become a little bit more than $200 for the first time. Okay. Now the next thing would be this. We'll discuss. It's exercise 6, sorting algorithm. Let me discuss the sorting algorithm in some detail, and then maybe we can solve a particular question. Sorting algorithm is a very nice tool, and it's actually used on computers all the time, and it's really a very basic and very nice thing installed in many different applications. So what is the question here? Problem: sort a given list of distinct real numbers. Doesn't have to be distinct, but let's assume that they're distinct for simplicity. Real numbers algorithmically. So in other words, find a nice procedure. So you are given, for example, so you are given a bunch of numbers. Let me take integers for simplicity, say. So 6 numbers here. Okay, so I'm giving you, I don't know, 5, 6, 1, 2, 3, 4. So this is a permutation, but I mean, for my application, it doesn't matter. Can be any real numbers. So I want to find a procedure which will allow me, say, to sort them in the descending order, just descending order, meaning that the next number is strictly smaller than the previous number. So how would the computer do this? So a computer takes two consecutive numbers. So 5 and 6, it starts from the beginning of the list. It looks at two numbers, 5 and 6. And 5 is smaller than 6. So she will sweep them around. So after the first step, you'll get 6, 5. 1, 2, 3, 4. So now it's called also bubble sorting because this 5 will be like a bubble. So we're here. Now, so in the first step, we were looking at the first two numbers, and they were not in our chosen order, and we will switch them around, and our bubble would be at number 5. Now we're looking, comparing 5 and 1. They're in good order, so 1 is smaller than 5, so this bubble will move here. So we're now looking at the same sequence of numbers, 6, 5, 1, 2, 3, 4, but we're comparing this guy and the next one. We're comparing these two. 2 and 1, they are not in the order, so we'll sorry. So we'll be changing places. So we'll have 6, 5, 2, 1, 3, 4, and the bubble is here. Now we're comparing 1 and 3, not a good order, so we'll switch places. 6, 5, 2, 3, 1, 4, and the bubble is on 1. We're comparing 1 and 4. Okay, not a good situation still. So 3, 6, 5, 2, 3, 4, 1, and the bubble is here. Once the bubble reaches the last position, we are not doing anything with it. So we are having a similar problem, but with an array consisting of one less number. So, and we start this thing again from the beginning. So we're putting the bubble. So this last position we can just forget for the second. And we are starting our bubble procedure from the 6. 6 is nice. So we are moving the bubble to 5, 6, 5, 2, 3, 4. And here we have our 1, which is fixed now once and forever. So we're comparing 5 and 2, still good. The bubble is passed on, 6, 5, 2. The bubble is here, 3, 4, and 1 is fixed. Now we're comparing 2 and 3, not good. So we have to switch them around, 6, 5, 3, 2. The bubble is here in 4 and 1. Now we're comparing 2 and 4. Yes. 6, 5, 3, 4, 2, and the bubble in the last position. So we are freezing now these two numbers at the end. So now these two are fixed, and we're happy. Now, when the bubble is at the last position, we are throwing it at the first position, starting from here again. So comparing 6 and 5, okay. So bubble moves one place here. 5 and 3, okay. Bubble moves here. Now, finally 5, 6, 5, 3, 4, 2, 1. So we have to switch those things around. And we are finally done. We have sorted our original sequence to a sequence in strictly ascending order. So this is this procedure. And the question is, what is the maximal number of swaps, of interchanging of two two neighboring numbers in a sequence we have to do in order to sort out the whole thing. And the answer here is it's our previous example. In fact, it would be the binomial coefficient. Okay, the maximal number of how it's called, transposition. So transposition is just interchanging two neighboring numbers. Required to completely sort out n real numbers and distinct real numbers is what? Let's see. I think it's n choose 2. Yes. And why is that? So we have to, if we start with the first number, then we can maximally switch it 1, 2, 3, n minus 1 times. Yes, so which is, okay, let's see, which is 1 plus 2 plus 3 plus plus n minus 1. And this sum is the first plus the last, and the number of entries and 1/2, yes. Okay, so how can we prove that? Yeah, so the idea of the proof is so that when sorting that an equals an minus 1 and plus n minus 1. Why? So how have we done this algorithm? So we start with the first number. In this case, it was 5, and we were looking how many maximal number of times we have to switch it with a neighboring number before it stabilizes. And so our sorting bubble, it started at the first position, and it can move maximally n minus 1 times to get to the last position. And when it's there, it's at the last position. So we're in the situation, so when the sorting number comes to the last position, that means that we'll place 1, the least number in our list, in the very last position. And we can forget about the least entry, and we have the situation with n minus 1 numbers which we can sort. And the worst case scenario, of course, for the sorting algorithm is, so worst case scenario is, of course, when we have the numbers in all increasing order, and then we actually need n choose 2 swaps of consecutive numbers in our sequence to get them in the reverse order. So it's, of course, 1, 2, 3, 4, 5, for example, 6. Now, if we want to sort this guy in the descending order, we'll have to move We have to use 5 steps. 5 steps. 2, 2, 3, 4, 5, 6, 1, and this guy would be frozen. Then we have to go 4 steps. 2, 3, 4, 5, 6, 2, 1, which will be frozen. Then we have 3 steps. 2, 4, 5, 6, and then 3, 2, 1. Then we have 2 steps. 2, 5, 6, and then 4, 3, 2, 1. And finally, we have one last step to sort the whole thing completely. And if we check the number of steps here, n equals to 6. And we have A6, which is the number of swaps we have done. 5 plus 4 plus 3 plus 2 plus 1, which is, what do I say, 6 choose 2, which is 6 times 5, 1/2, which is 50. And that's this sum, of course. Okay, now it's definitely time for a break now. Let's make it, I don't know, yeah, 5 minutes, and then we'll continue with recurrences of order 3 with constant coefficients. Okay, good. A small break and see you soon. 3. And we'll be concentrating mainly on recurrences with constant coefficients, except they might be non-homogeneous, and in this situation we still get very nice closed formulas for those. Let me start sharing the screen. Yeah, good. Recurrences. Okay. So second order recurrences with constant coefficients. And the Fibonacci numbers, which we discussed a little bit last hour, will be a good example of those. So what do we have? So the basic definition is so we're looking at relations of the form C sub k a n plus k plus c k minus 1 a n plus k minus 1 plus and so on plus say c naught a n equals some right hand side f of n, and here n is at least k, and we have the initial condition. So we have to fix a 1, maybe, I don't know, so it don't quite, okay, so we have to fix the first, we have to fix the first k of them, yes, and this would be a1, a2, a3, and so on up to ak. These are fixed. And once we have them, we can use our recurrence to get ak plus 1, ak plus 2, and so on. So if f of n is identically 0, then the recurrence is homogeneous. And the typical example of that was this Fibonacci recurrence an plus 1 equals an plus an minus 1, or in other words, an plus 1 minus an minus 1 equal to 0. It is homogeneous because this guy is, the right-hand side is 0 for all n. Okay, so let me start with some general lemma saying, and you have probably seen this already, such a lemma in linear algebra, maybe solving non-homogeneous systems of linear equations. And maybe if you have worked with linear differential equations of second order or any order, you have seen similar statements. So a general solution to a non-homogeneous recurrence equals a general solution to a non-homogeneous, to a homogeneous recurrence plus a particular solution to a non-homogeneous recurrence. So if we know just one solution to a non-homogeneous recurrence from somewhere, then we can usually get the general solution of the homogeneous recurrence. So homogeneous recurrences are much easier to handle. And then adding this particular solution of our initial problem to a general solution of the homogeneous problem, we can get all solutions of the original non-homogeneous problem. And the proof is just, which is equivalent to, the statement is equivalent, the difference to the following statement, the difference of two solutions of a non-homogeneous recurrence satisfies the homogeneous recurrence. And this is obvious by linearity. Satisfies a homogeneous recurrence. And this is obvious if we just subtract two solutions to the non-homogeneous recurrence. The right-hand side will disappear, will become 0, but the left-hand side would be exactly the same. So I will not dwell too long on this thing, because as I said, it appears it's the same thing, the relation between the homogeneous and non-homogeneous problems, which you have probably seen in many, many different places. So we start with homogeneous recurrences with constant coefficients. So this is a very kind of useful, but also fairly trivial class. Okay, so those are of the form CK. What did I had? What was the notation? A n plus k plus ck minus 1 a n plus k minus 1 plus da 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 plus c naught a n vanishes. So, and C0 to Ck are constants, and we are looking for sequences A1, A2, and so on, AN, and so on, satisfying such a thing. And again, the idea is we can guess a whole bunch of solutions to such a recurrence. Okay, so guess, substitute AN in the form some constant, say capital A times R power N, and find appropriate R. So making this ansatz, AN equals R, capital R, we are substituting a solution in another form, in other words, in form of a geometrical progression. And we are looking what denominators of a geometrical progression will work for our specific recurrence relation. Okay? So if we do such a substitution in our equation, we get, so we get that R should satisfy the following linear equation. Ck R power k plus Ck minus 1 R power k minus 1 plus da 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 plus C naught vanishes. This is called the characteristic equation. Of, let me denote my linear recurrence by asterisk or star. So it's just an algebraic equation of the same order k. And now, if we think a little bit, we can conclude the following. So, remark. So let me denote this by double star, maybe. If double star has k distinct solutions, say call them R1, R2, and so on, Rk, then a general solution of star, our original recurrence, is of the form, let's see, what do I want to say? Yes, AN equals some constant alpha 1 R1 power n plus alpha 2 R2 power n plus da 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 plus alpha k Rk power n, where alpha 1, alpha 2, alpha k are arbitrary constants. There is a little problem with my remark, though, is that what I'm saying works over complex numbers. So this is true over complex numbers C. But in many cases, we'll be interested in real solutions to real recurrence relations. And it can very well happen that even if this characteristic equation, double star, has real coefficients, its zeros are complex conjugate numbers. Some of its zeros are complex conjugate numbers. So we have to think a little bit more if we are interested in real solutions or to real recurrence relations. But over complex numbers, if we don't care about our solutions being real and complex, as soon as we get that our characteristic equation has as many distinct roots as its degree, then we're happy. We're done in a sense by this nice formula. Okay, so let me first describe and maybe make some examples, find some examples of the cases. We'll be mainly working with recurrences of order 2. So for recurrences of order 2, so we have quadratic characteristic equations. So in other words, we have, what do we have? C2r squared plus C1r plus C0 equal to 0. And if C2, C1, C0 are real numbers, so let me call this maybe by plus, then there are 3 basic cases for plus, namely case 1, 2 distinct real zeros, case 2, 2 complex conjugate zeros, and finally case 3, a real double root. And we'll discuss what happens in all these 3 cases, and we'll give some examples. Okay, so, okay, case 1, 2 real distinct zeros. So, and in this case, what I said before works perfectly. Lemma, a general solution of the recurrence is of the form what do I have? An equals alpha r1 power n plus alpha 1 plus alpha 2 r2 power n. 2 real zeros, say r1 and r2. And if we want complex solutions, we will allow R1 and R2 to be complex numbers. If we want real solutions, we only allow, what do I say, lambda. I mean, if we want real complex solutions to our recurrence, we'll allow lambda 1 and lambda 2 to be complex numbers. If we want only real zeros, we allow lambda 1 and lambda 2 to be real numbers. And this is it. Nothing else is necessary to cover the whole set of real solutions. So that, let's do our basic example, Fibonacci. Fibonacci, what do we have for Fibonacci? Fibonacci is an plus 1 equals an plus an minus 1. And the initial condition is a0 is 0, a1 is 1. Okay, so let's first look at the recurrence relation. So the recurrence relation, the characteristic equation. What do we have? So I start with the recurrence. I'll be moving all terms in one side. We have this thing, vanishing, and the characteristic equation would be 1 times r squared minus r minus 1 equals to 0. R squared minus 1 vanishing. So what kind of roots does it have? We're using PQ formula, which is 1/2 plus minus the square root of 1/4 plus 1. So this is positive. So we're in this situation with two real zeros. We'll be getting 1 plus minus the square root of 5 divided by 2. This is exactly the golden ratio thing. If you don't know this, it would be probably nice to check what the golden ratio is. Okay, so we have R1 equals 1 plus the square root of 5 1/2, and R2 is 1 minus the square root of 5 1/2. So we also have those initial conditions, and we want to write down our entries in terms of alpha 1 R1 power n plus alpha 2 R2 power n. So the general solution is, so an equals alpha 1 R1 power n plus alpha 2 R2 power n, and we want to choose alpha 1 and alpha 2 from the initial conditions, Okay, so if we use n equals to 0, so a0, which is 0, should be equal to, so this would be 1, so alpha 1 plus alpha 2. Because 0th power, any number, any real number is 1. Okay, so we have a1, which is 1, should be equal to alpha 1 times r1, which is 1 plus the square root of 5 over 2, plus alpha 2 r2, which is 1 minus the square root of 5 over 2. So what do we get here? If we multiply this second equation by 2, we get 2 alpha 1 plus alpha 2 plus alpha 1 square root of 5 minus alpha 2 square root of 5. Yeah, that's it. And now from the first equation, this is 0. So we're finally getting the following system of relations for alpha 1 and alpha 2. The sum vanishes. And if we divide by the square root of 5, we get alpha 1 minus alpha 2 is 2 divided by the square root of 5. Yeah. Say if we substitute alpha 2 equals minus alpha 1 from the first equation in the second, we'll be getting twice alpha 1 equals twice 2 divided by the square root of 5, which means that alpha 1 is 1 of the square root of 5, and alpha 2 is minus the same thing. So our Fibonacci numbers will be getting a rather odd form. So an would be what? 1 plus the square root of 5 over 2 square to the nth power times 1 over the square root of 5 plus a similar expression. And here I'll change to the minus sign here. So this is another expression for the square root for the Fibonacci numbers, but in this form you can hardly recognize that all the Fibonacci numbers are in fact nice positive integers. But there is also a way to rewrite this in a little bit different form, which is nicer, and you can recognize many of the standard properties of the Fibonacci numbers from a somewhat different form. And there was a French mathematician at the end of the 17th, beginning of the 18th century, who spent a lot of time getting nice properties of Fibonacci numbers. His last name was Binet. He also made interesting contribution to both combinatorics and linear algebra. Okay, so let me do small.
Just a question. What did you write between in the middle there?
Just
below
a minus.
Fibonacci. It's minus. Okay,
yeah, it's just a minus. I'm sorry. Let me do it. Yeah, it's just a minus sign. Just a minus sign here. Jean Binet, if I remember correctly. Jean Christophe or something. Jean Baptiste Binet. Don't quite remember. Okay, so now we still have to treat. How much time do we have? Oh, about 15 minutes. Good. We still have to treat case 2 and case 3. And case 2 is two complex conjugate roots. Okay, let's see, what can I say in this case? I had a small lemma somewhere about that. 1 second. Where was it? Yeah, okay. So in this case, again, if we care about complex solutions, the same formula as before works. But if we want real solutions in the situation, yeah, then we should do the following. Yeah, so complex conjugate. Okay, so say we call those guys R1 and R2, and we have R1 equals R2 complex conjugate. So let me denote the absolute value by L. So denote the absolute value by L, and the argument of lambda 1 will denote by alpha the argument of lambda 1. The angle, in other words. So lambda 1 equals L e power I alpha, where alpha, we can assume that alpha 1 lies in the upper half plane, which means that lambda 1 is in between 0 and pi. So lambda 1 is here, and lambda 2 is in the lower half plane. Okay, now the claim is that then you can write n in the form L, some constant k1 times cosine of n alpha plus k2 sine of n alpha. And k1, where k1 and k2 are arbitrary real numbers. I don't know why in my notes we have L here, because L can be incorporated in K1 and K2, but the claim is that, yeah, Yeah, I guess this is it. So, yeah. Okay, and finally, the last case, and if we have some time, maybe we can do some examples, is that two coinciding real roots R1 equals R2, say, yeah, R1 equals R2, say equals to some number R. And in this case, then we have the following. AN equals C1 R power n plus C2 n times R power n. Again, C1 and C2 are any real numbers. Okay, maybe we can do some examples. So how do we get, say, in the third case? Case 3, maybe what kind of recurrence relation will lead us to a double root? So if we think an plus 1 minus 2an plus an minus 1 vanishes, for example, then the recurrence, the characteristic polynomial would be r squared minus 2r plus 1 vanishes, which is r minus 1 squared vanishes, yes. So, and then I'm saying that the answer to the general formula for the entries of my recurrence should be in the form C1 plus C2 times n, because r equals to 1. So this is a general formula. Let us check that this works. Checking. So I'm saying that any real constant C1 and C2 here in this linear function will provide us, will satisfy this recurrence. Let us check. Say an minus 1 would be C1 plus C2 times n minus 1. An is as above C1 plus C2 n. And finally, Cn plus 1 is C1 plus C2 times n plus 1. So let's substitute in the recurrence. So we want to check that an plus 1 minus twice an plus an minus 1 should vanish.